In this video, we're going to start to look at these new compound angle identities. I think the first time you see these, you can be a little bit daunted by them. So I'm just going to look at like a couple of simple applications before we get stuck into the exam style questions. Luckily for you, we get them in the formula booklets. Okay, there is a proof of where these come from in the A-level maths textbook, and it basically just involves a couple of right angle triangles and some Pythagoras and the socket tower. I'm not going to go through the proof now, but you will be shown this proof in A-level maths. Okay. So what's going on with these mad identities? Like, the first thing to realise is that what it's telling me is if I've got the sign of an angle plus another angle or an angle minus another angle, we can treat this, remember the 3 equal signs means it's identical to, it works for any value. So sine of like a plus b would be the same as sine a cos b plus cos a sine b. Notice, be very careful with the way that the plus and the minus is orientated, because it does change here. So if I was going to do cos of a plus b, that would be cos a cos b minus sine a sine b. Okay, so let's do a couple of questions involving using these identities to see what's going on. I've drawn 2 triangles here. You should hopefully be familiar with these triangles. These are from GCSE maths. Basically, these are like the common ratios that always come up, like 30 degrees, 60 degrees, 45 degrees. A lot of questions will involve those angles. And the reason is you get nice trig ratios when we do this. Okay, so if I didn't have a calculator and I said, well, what's sine of 15 degrees? Now, we can do that without a calculator, just from knowledge of these identities and these 2 triangles. Okay, so I could say, well, sine of 15, that would be the same as sine of 45 minus 30. And then I could compare that with this identity, because I've got sine of a minus b. Okay, so that would be equivalent to sine of a minus b is sine of a cos b, so that would be sine of a, which is 45, cos of b, which is 30. It might be better actually, while we first see this, if you understand that I'm comparing that with sine of a minus b, where a is equal to 45 and b is equal to 30. Okay, so that would be sine a cos b minus cos a, so that would be cos 45, sine b. And if we understand these triangles, or remember these triangles, then I could remember what these ratios are. So sine of 45, look at the 45, opposite over hypotenuse, that would be 1 over root 2. Cos of 30, cos is adjacent over hypotenuse, so that would be root 3 over 2, minus cos of 45, which is cos again. Cos and sine of 45 is the same, they're both 1 over root 2, but if you think about it, you can use either 45 here. Cos is adjacent over hypotenuse, so 1 over root 2. Sine of 30, 30 degrees, sine is opposite over hypotenuse, so that would be 1/2. You notice that we can take a common factor of 1 over root 2 out. And that would leave me with root 3 over 2 minus 1/2. I probably could have rationalised this straight away, but I'm going to rationalise it now. So if I multiply the top and bottom by root 2, I'd get root 2 on the top. And root 2 times by root 2 on the bottom would be 2. And look inside this bracket, we've got a common denominator, so it would be root 3 minus 1 all over 2, which we could then expand the top and the bottom. Root 2 times by root 3 would be root 6 minus, oh, excuse the stomach, root 2 times by minus 1 would be minus root 2 all divided by 4. So without using a calculator, we can get an exact expression for different angles, sine of 15 degrees. Okay. Maybe pause and try to do the same for cos of 105 degrees. So think about how we can get 105 degrees using these angles that we already know about. Okay, so 105, how are we going to get that? We could write it as cos 60 plus 45. And then obviously for this one, we're going to be using cos of a plus b, where a is equal to 60 and b is equal to 45. So we could write this as cos a plus b, cos a cos b, so cos 60, cos 45. Be careful here, plus becomes minus for this identity. Sin a sin b, so sin 60, sin 45. Okay, so cos 60, 60 adjacent over hypotenuse, so that'll be a half. Cos of 45, 1 over root 2, minus sine of 60, 60 sine is opposite, so root 3 over 2. Sine of 45, again, is 1 over root 2. So we can take a factor of 1 over root 2 out. We'll be left with 1/2 minus root 3 over 2. Rationalise, so that'll be root 2 over root 2 times root 2, which is 2. Combine your fractions, common denominator, 1 minus root 3, divided by 2. I nearly wrote 4, then it'll be 4 when we multiply out, but obviously when you subtract fractions, you just subtract the tops. And then expand, so that'll be root 2 minus root 6 over 4. Okay, this is not a common exam style question. Obviously, if it said work out cos of 105 degrees, you can just type that into your graphical calculator, can't you? But I just thought instead of jumping straight into like the exam style questions, just nice to take this back to what trigonometry is about. It's just about these right angle triangles, and this is just a new set of identities that we get given in the booklet that we're going to need to use. And the thing about these identities, there's actually a couple of different applications that we're going to be looking at over the next 2 weeks. Okay, so it's quite important that we get familiar with these before we move into the questions. Okay. Okay, so a good application of these identities that we do get in the formula booklet is we can now get expressions for double angle identities. We don't get these in the booklet, so we're going to have to remember these. Okay, so if I said, well, what is sine of 2 theta? We can use this property for a plus b to help us to write this in a different way. Just think about 2 theta as theta plus theta. And then we've got sine of a plus b. A and b, in this case, are both theta. So that would be sine theta cos theta plus, because we're using sine of a plus b, cos theta sine theta. So obviously to simplify, we know that sine 2 theta is the same as this plus this. Well, they're both the same, aren't they? So that would be 2 sine theta cos theta. You want to highlight that in your notes. Like, that is a very important identity that will come up a lot within questions. Okay, pause the video, try and do the same for cos 2 theta and for tan 2 theta. Cos 2 theta is a bit of a sneaky one. There's actually 3 different versions I'm going to end up with for this, but maybe pause and see if you can get there first. Okay, so for cos 2 theta, we can write it as cos theta plus theta, so we're using cos of A plus B, and both of them in theta. That would give us cos theta minus sine theta. So we could obviously say that cos 2 theta is equivalent to cos squared minus sine squared. That form of the identity is actually not very often used at all, okay? Because we've got an expression with cos squared and with sine squared in, obviously we know that 1 would be equivalent to sine squared plus cos squared. So we can use this identity and combine it to get an identity just with cos squared in and an identity just with sine squared. So we could write it as cos squared minus sine squared. Now sine squared would be 1 minus cos squared. So we could get a more useful version of this identity. Minus minus becomes plus, so cos squared plus cos squared would be 2 cos squared theta minus 1. Okay, we can also go back to this line, and instead of getting everything in terms of cos squared, we can get everything in terms of sine squared. So we could replace cos squared with 1 minus sine squared minus sine squared. So that would be equivalent to 1 minus 2 sine squared theta. And you'll see why these different versions are really useful. Okay, last one we'll do will be tan 2 theta. Okay, so finally we got tan 2 theta with tan theta plus theta, so we're using tan of A plus B. So we can write that as tan theta plus tan theta all divided by 1 minus tan theta times by tan theta. So obviously that would give us 2 tan thetas all divided by 1 minus tan squared theta. Okay, so that gives us all of the identities and a brief sort of understanding of why they're useful. In the next video, we'll do some exam style questions using these identities. Okay, thanks guys.